And this might not take all class, so we might have time towards the end for questions, but I feel like I say that a lot and then it never happens. So, but we kind of skipped over this one to talk about inflection points, so we've got to go back to this one. So we have the value of an investment at time t is given by S of t, and the rate of change S prime of t is given in the graph. Sorry, I just saw the thing in chat. Is Zach here? Yeah, he is. Okay, cool. Just sorry. Jay, is the review similar to the exam? I would say yes. I mean, that's kind of what I rate them to be. So I would say the review up on Blackboard is probably the best way you can study for the exam, is to review that and make sure you can do all those problems really well. But just like last time, your exam is partially multiple choice. There's going to be some of those find the error ones again. There are some of those in the practice and some free response. All right, now let's jump into this. So we have this investment is given by S of t, but notice that the graph we're given isn't S of t, we're given S prime of t. So we're given the derivative graph, but we still want to talk about the normal one as well. So the first thing we're asked is to find where the critical points of S of t are. So remember, the critical points of S are, of S of t is going to be when the derivative equals 0 or undefined, but since we have a continuous function here, it's never undefined, so we don't need to worry about that. So essentially the critical points of the original function is going to be where this derivative is going to be equal to 0. So we have it here, here, right here, essentially where it touches the x-axis, t-axis in this case. So you'd get t equals 1, 4, and 6. Sorry, 1 second. So those would be our critical points. And now I want to identify each one of the critical points as either a maximum, a minimum, or neither. And that goes back to essentially the relationship between the original function and the derivative. So remember, let me just scroll back up and get to it. Remember when we talked about whether or not a point's going to be a max or a min when we were looking at the derivative sign charts? We don't have a sign chart here, but this is kind of what we're working with. We're working with is the derivative negative and then changes to positive, or is it positive and then changes to negative? So remember, kind of each one of these cases, we have that it's either a max or a min, and it kind of depends on which way it changes. So let's go back and let's look at that graph and kind of see where it's positive and where it's negative. So if we look at this graph, and we kind of can split it up at 4 and 6, we have this whole first part is above the x-axis, so that would mean that this derivative is positive. And then between 4 and 6, the graph's below the x-axis, so we would have that the derivative is negative. And then the derivative turns out to be above the x-axis, t-axis, again, in that kind of last piece. So essentially, let's look at each one of these critical points separately and kind of figure out which type of thing it is. So let me also do this. Negative, positive. Nope, I'm backwards. Positive, negative, positive. So notice that t equals 1. It doesn't actually cross the t-axis there. It kind of just touches it, and then the screen is black. That's not good. Let me reshare. Blink. Is it not black now? Hooray. What was I saying? Oh, t equals 1. It kind of touches the t-axis, but then stays above the t-axis. It never actually changes to below the t-axis. So since the derivative doesn't actually change sign at t equals 1, this would be neither. Whereas with t equals 4, the derivative starts out negative to the left and then turns, it starts out positive on the left and then negative on the right. Goodness gracious. So since it starts out positive, that means our original function would be increasing. and then change to decreasing. So if we start increasing and then we change to decreasing, that would turn into a maximum. And that's also the relationship where if the derivative changes from positive to negative, it's a max. So we would have a maximum here. And I'll just remind us that S prime changes from positive to negative. And then at 6, it starts out below the x-axis, so the derivative starts out negative, and then it crosses to be above the t-axis. So it would be positive. So if we start with the derivative being negative, the original function is decreasing and then changes to increasing, which must have made it a min. So we have a minimum here since S prime changes from negative to positive. So that kind of relationship between the derivative value and how the original function is behaving is highly important to be able to figure out whether or not these turns into maxes or mins. You can kind of memorize the kind of order if you want to. You could memorize that changing from positive to negative makes it a max and from negative to positive makes it a min. But I personally, myself, still do this where I think about, okay, the derivative is positive, so the original is increasing, and then it's negative, so it's decreasing. And if you watch my little tiny video, you will constantly see me do these little, hand motions of increasing versus decreasing. My professors used to look at me like I was insane. But I think that's the easier way to just talk yourself through it, but whatever floats your boat. Questions, concerns on that one before we go over to more examples? All right. So then the last two we have to walk through are essentially the same type of idea. Find all extrema and inflection points. So this is kind of using all of 4.1 and 4.2 in this one example. So find all extrema and inflection points. So I'm going to, yes, this is essentially these last two examples are the last thing we have to go through. And we've technically finished up all the content. We're just going to see two last examples of how we're going to use it. So find all extrema. So remember, extrema is a fancy word for maxes and mins. So the first thing we need to do is find the derivative. Why is that so shaky? F. There we go. So we need to find the derivative. Now notice that this is a product rule. So we would have x times e to the x. So if maybe I come off to the side really quick up here and do my little chart, and I'll do it over here so that I don't run out of space later on. So if we do our little product rule chart, if you will. Oops. So x and then e to the negative x and then 1 and, well, we'll talk about this other one. So e to the negative x is technically a chain rule. So we would have the derivative of e to the something is e to that something, but then we have to take the derivative of the negative x, which will get us, whoa, which will get us -1. So then if we put it together using our product rule, f prime g plus fg prime, we'll have 1 times e to the negative x, so I'll just write e to the negative x, plus x times negative e to the negative x, essentially. So e to the negative x minus x e to the negative x. Now, the next thing we would have to do is we would have to set this equal to 0 and see if it's ever undefined. The first thing that really helps with the ones that have e to the whatever in it is pretty much all the time, all of those terms are going to have an e to the whatever in it. So we're going to go ahead and pull that out. So these both have an e to the negative x in it. So we're going to pull that out. So the first term would be 1, because remember, there was something that we pulled it out of. And then minus x. And Oh my goodness. So this, once we reduce it that tiny little bit, is going to help us with the setting it equal to 0 idea. Now, while I would personally leave it like this, I do want to say something because I'll have to talk about undefined. Remember that a negative exponent means that it would be a positive exponent in a denominator. So technically, this is equivalent to 1 over x e to the x. So technically, we have a denominator in this derivative, so we have to consider undefined. That's the reason I bring it up. So the next step that we would do to find extrema, remember these ones do get a little long, is that we would want to set the derivative equal to 0 and find if it's ever undefined. So let me talk about undefined first, because that's kind of the easier one. So, well, maybe not easier one, but I will tell you that e to the x or e to the anything is never 0. So this function is never undefined. So that's actually one of the really nice things about e to the something, is it's never going to be equal to 0. So it's never really going to give you anything of use. So if we wanted to set the derivative equal to 0, that would mean that, so let me go back to kind of using this form again. So pretend we didn't change it over to a fraction and we're looking at the e to the negative x times 1 minus x form. Since that's a product of things, we would need each piece set equal to 0. Now this I just said never happens. E to the anything is never 0. But 1 minus x being equal to 0 would give us that x equals 1. So essentially the only critical point we have in this derivative, from this derivative I should say, critical point. That's the only critical point we've gotten. And it's the only critical point this function will have. I need to start being a little careful also around space. How much more space do I have? I should be okay. So at this point, once you've found the derivative and you found the critical points, you get to choose which kind of which derivative test you want to use. I'm going to go ahead and just use the first derivative test. We are going to find the second derivative for the inflection points. So this would be a case where using the second derivative could possibly be good. But I'm just going to use the first derivative test. I feel like it's the one that most people default to. So I'll go ahead and do it. So we plug our critical point on that number line, and then we pick some test points. I haven't seen any questions, but once you have a question, please tell me. Please feel free to interrupt me. So we need test points, so we need something less than 1 and something greater than 1, and you can pick whatever numbers you want. So I'm going to pick 0, and I don't know, I guess I'll just go with 2. And we're going to plug both of those into the derivative, so we need to find f prime of 0 and f prime of 2. I'm going to use that e to the negative x times 1 minus x form again. So we'll get e to the 0 times 1 minus 0. This is another situation where I personally would just look at the sign instead of figuring out the number. Remember, I've said that you don't actually need to figure out the number. You just need to figure out the sign. And the other nice thing, kind of side note up here, is that e to the anything is always also greater than 0. So unless there's a negative in front of the e, no matter what that exponent is, that e thing is always greater than 0. So technically this thing would be greater than 0, whatever the heck it is. I'll find out what it is for anyone who wants to. Well, it's going to be equal to 1. So this value would be equal to 1 if you were to punch that into a calculator. But you can also just say the e to the 0 is going to be positive, 1 minus 0 is positive, so that piece is positive. Remember, you can kind of just do that kind of sign way. And then if we have 2, well, this would be a positive thing times a negative thing, so I know that that's going to be less than 0, but if you're curious, the actual number is negative 0.135, blah, blah, blah. So we have a positive value when we plugged in 0 and a negative value when we plugged in 2. So I like to draw my little, line segment line kind of deals. So if the derivative is positive, the original function is increasing. If the derivative is negative, the original function is decreasing. So since the original would therefore change from increasing to decreasing, we must have a maximum at x equals 1. So we have a local maximum at x equals 1. We're not done this problem yet, but we've done the first half. But I'll pause for a second and see if there are any questions. But I'll also continue to babble a little bit. So there's no local min for this one because there's nowhere that the derivative changes from negative to positive. And we only had one critical point, and that critical point can only be one or the other. And once again, I've said this before, but 98% of the time, we only care about the x value. If I want the y value, I will be very specific. Even Wiley will pretty much be very specific if they want you to say the full coordinate point where they want the y value as well. I'm not seeing any questions, so we'll move on to the inflection point part of this question because no, we're not done yet. So we've found all the extrema, and now we need to find the inflection points. I don't know what's going wrong with my English today. I keep saying the wrong thing. Inflection points. So remember to find the inflection points. That's what the new thing that we talked about on Friday. This is where the second derivative changes sign, where the original function changes concavity. So we need the second derivative. For finding the second derivative, you can use whatever form of the derivative you want. But I'm going to go back to this kind of first form of the derivative and use that to find the second derivative. If you used this e to the negative x times 1 minus x, you totally could. That would be a product rule. Well, what we're going to do is going to include a product rule. But I'm personally going to come back to kind of this slightly more unsimplified version and use that to find my second derivative. So let me try to keep that in there while I find the second derivative. So if we find the second derivative, first thing we need is the derivative of e to the negative x. So we'd get e to the negative x times -1. So I'm going to go ahead and put the negative in the front. Hopefully that's okay, because that would have been a chain rule. And then we have to add that to the derivative of x times -e to the negative x. Well, maybe I should have went to this slightly more simplified form, but I've already committed. So that would be a product rule. So if I kind of come off to the side and do my little chart. So I've committed to x and -e to the negative x. But anyway, so the derivative of x is 1, and then we'd have -e to the negative x times -1. So just positive e to the negative x. Ooh, it lagged a little bit. There we go. So if we put that together using our product rule, f prime g, so 1 times -e to the negative x plus x times e to the negative x. So now I can scroll down a little bit. Ooh, I do not have as much space as I thought I did. Oh boy. All right, it's okay. Notice, because I want to clean this up a little bit, I have -e to the x plus -e to the negative x. -e to the negative x minus -e to the negative, oh my god, -e to the negative x plus -e to the negative x. Good lord. So that combines together to give us -2 e to the negative x and then plus xe to the negative x. Just like last time, they both have an e to the negative x in them, so let's pull it out. So we'll have -2 plus x, or x minus 2 if you want to rewrite it. I would usually do that personally, but just to kind of keep it in the form that it's written in, I'll just leave it like that. Ooh, I ran out of space. Oh boy. It's okay, I'll figure something out. So the next thing, now that we have the second derivative, is we need to set it equal to 0 and find if it's ever undefined. It's never going to be undefined because the e to the negative x is never 0, and that would have been our denominator. I'm not going to write that because I don't have the space, but it's the same idea as last time. Is that's technically a denominator, but it's never a 0, so it's never undefined. And if we want the whole entire thing to be equal to 0, either e to the negative x is 0, which is never, or negative 2 plus x equals 0, which gives us x equals 2. And then I think I'll have to erase my little product full chart to give myself some space to finish this, because we're almost done this one. So now that I have, it's not exactly correct to call it a critical point, but that's kind of what it's like, but it's for our second derivative. So we draw a number line again, but we remember that this one is in terms of the second derivative, so we'll put that number on there. We'll choose some test points. Like I said, these do get pretty long and pretty tedious, but it'll be all right. If I plug in maybe 0 and 3 as my test points. Remember, we need to put them into the second derivative. I really needed to write smaller. Oh boy. So we'll get e to the 0 times negative 2. This will be a negative value. It'll be negative 2. So when I plug in 0, I get a negative. When we plug in 3, we'll get e to the negative 3rd times negative 2 plus 3 will give us 1. That's going to give us a positive value. What is the actual value, in case you're curious? 0.05 if I round. So that'll be a positive value. So essentially, our original function goes from concave down to concave up. So I like to put the little concave pieces in there. So since it changes sign, we'll have an inflection point at x equals 2. And now we're finally done that question. Like I said, they can get pretty long, pretty tedious. Questions, concerns on that one? This full, because someone asked how many of these will be on the exam. One this full, and by full I mean finding both the extrema and the inflection points, probably only one because of how long they take. There may be another question where I ask you to just find the extrema and not the inflection points, or one where I ask you to find the inflection points but not the extrema. But one where you have to do both of them for the same function, just once. Questions, concerns before we do one more? We'll grab that at the end, Kayla. Are there the same amount of questions on the exam as the review? No. I mean, one thing is that there isn't any multiple choice on the review. I haven't finalized your exam yet. I'm writing it currently and I'm not quite done yet. At the moment, 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like your exam's probably going to have about 15 questions. And the review had, I don't remember how many questions the review had. 12, but there were some with parts. And when I counted the 15 on the exam, it included parts. So there's probably a few more on the review than there will be on the exam. Anyway, So let's finish this last one. And then, well, these ones take a long time, so it might take the rest of the time, but if not, we'll have time for questions. So we want to find the extrema inflection points again. So the first thing is we need to find the first derivative. The nice thing here is that we just have a polynomial. There's no more product rules. There's no more e to the x's, anything like that. So bring the power down, we'll get 15 x to the fourth minus 15x squared. One tip I can give you for once you've found the derivatives is try to factor out as much as possible. Like whatever they have in common, pull it out. So both of these terms have a 15 and at least an x squared in them. So let's go ahead and pull that out. Let me go to the right so that I don't run out of space again. So they both have a 15x squared. So if I pull 15x squared out of 15x to the fourth, we'll get x squared and then minus 1. So once you find the derivative, you need to set it equal to 0 and determine if it's ever undefined. There's no denominator here, so this is never going to be undefined in that regard. If we want to set it equal to 0, and this is why I suggest factoring out as much as you can, because now we have a product of things. And remember, if a product of things is equal to 0, it must be true that one of the pieces is 0. So we can break it up into essentially when 15x squared equals 0, and then when x squared minus 1 equals 0. Also remember, I think I wrote it down the other day on a different one. Sometimes you might need to use the quadratic formula to find when a thing is equal to 0. But in this case, we would have that x equals 0 from the 15x squared piece. And then we'd have x squared equals 1, equals 1. So then x would be either plus or minus 1. Remember, whenever you square root something, you pick up a plus minus. So here, let me see how much space I have. Okay, I have way more space than the last one. Okay, cool. So here we have 3 critical points that we need to test. So once we have the derivative, we set it equal to 0. We found all the points. We gotta plop them on to a number line. Gotta choose some test points. This is the first one where we've actually had to choose a not super nice point because I need something between 0 and 1. So I need to choose like a fraction. So I'm going to choose 1/2, so 0.5 and negative 0.5. It's like the nicest number I can choose there, I guess. And then I need something greater than 1 and less than negative 1. I'm going to go ahead and do 10 and negative 10 because I can. You can choose whatever number you want, but again, sometimes going a bit obnoxious can make the signs easier to tell. So we need to plug all of those points into the derivative. So first I'm going to do my little sign idea. And then I'll tell you the actual number. Those numbers are going to be pretty large now, but I chose negative 10. Oh well. But if you think about these in terms of just the signs, that 15x squared piece is always going to be positive because anything squaring any number is a positive number and multiplying it by a positive 15 would give you a positive number. So all of these are going to start out as a positive times something else. So positive times positive times. So no matter what number I plug in, that 15x squared is always going to be positive. And again, I'll find the actual numbers in a second in case you don't like this type of idea. And then the x squared minus 1. Well, the x squared is always going to be positive. So if I plug in negative 10, I'll have 100 minus 1. So that'll be a positive number. If I plug in negative 1/2, I'm going to get positive 1/4. So 1/4 minus 1 is going to lead me to a negative number. So I'll get a negative there. Same thing when I plug in positive 1/2, I get 1/4 minus 1. I'm using this 15x squared times x squared minus 1. If you want to use the unsimplified one and just plug in the number, that's perfectly fine. And again, I'm going to write down the actual number in a second. I'm just doing my little sign idea in case anyone likes to do those. And then if I plug in positive 10, we'd get a positive number there. But anyway, what are our actual numbers here? So we have 15 negative 10 squared times negative 10 squared minus 1. This is 148, 500. This will also be 148, 500. This will be 15 times negative 0.5 squared times negative 0.5 squared minus 1. This will be negative 2.8125, and this will also be negative, because essentially they're the same thing. Is it possible to use x squared minus 1? You can't just take the one piece of it, because then you're not taking into consideration that 15x squared. Now, the coincidental thing is if you had taken x squared minus 1, in this case, it wouldn't make a difference. But say that was just a 15x instead of a 15x squared, then that would change the signs of all of these answers, and so we can't forget it. So you always want to use the entire derivative, not just one piece of it. So we get that the derivative sign chart will look like a positive value, negative, negative, positive. So if we do our the little line segments that I like to do, we have that the original function is increasing and then decreasing, but then decreasing again and increasing. If you like to do something where you would like to continue it down, if you want, instead of having to move it back up like I do, whatever floats your boat. So remember that we're only going to have a max or min if it changed sign. So x equals 0 is going to give us nothing. But at x equals negative 1, it changed from positive to negative, so that will give us a maximum. So we have a local max at x equals negative 1. And a local, over at positive 1, we changed from negative to positive, so that'll give us a min. So we'll have a local min at x equals positive 1. Questions, concerns on how I got that? We haven't done the inflection points yet. Okay. I'll hold on 5 more seconds and then we'll do the inflection points. All right, so to find the inflection points, we need the second derivative. Whoa. We need the second derivative. Kind of like the first example, I find it easier, come on, keep scrolling, to kind of go back to this unsimplified answer and use that to find the second derivative, because if I use the 15x squared times x squared minus 1, I have to use a product rule. And if I just use the 15x to the fourth minus 15x squared, it's just power rules. So we would get 15 times 4 gives us 60x cubed minus 30x. Once again, I personally suggest factoring out whatever you can. So they both have a 30x in common, which will give you 2x squared minus 1. So now we have to find where this derivative, second derivative, is equal to 0 or undefined. So we need to set it equal to 0. I'm still running out of space again. This is never undefined because, again, there's no denominator floating around anyway. And then for setting it equal to 0, we kind of have that case again where we kind of split it up into pieces. So 30x equals 0 is going to give us that x equals 0. And now we're going to encounter our first kind of really gross, not really gross, but kind of gross answer for x. We take the square root here, we'll get plus minus the square root of 1/2. I'm going to leave it like that. I know technically people say you shouldn't leave a fraction as a square root because there would technically be a square root in the denominator and you should rationalize, but that's algebra stuff and we're in calculus. So we won't care. So we have our second derivative number line. This one might have been a nice one to do the second derivative test on. Maybe I should have done the second derivative test. Oh well. So we have negative square root of 1/2, 0, and positive square root of 1/2 on here. Now, square root of 1/2, if I remember correctly, yeah, these are approximately like 0.707, because we kind of need to know that to choose our test points. So we got to choose some test points, so I'll pick 1/2 and negative 1/2 again, because that's really the nicest number in those sections. And then, whoops, I don't know, I think I'll just pick 1 and negative 1 for the ends. It doesn't matter what number you pick. And we've got to plug all of those into the second derivative. I'm running out of space, so I'm just going to write down the signs, whether it's positive or negative. And by that I mean I'm going to write less than 0 or greater than 0. And, well, no, here's what I'll do. I'll write down the number. Let's just not be lazy and I'll write down the number. So we have 60 times negative 1 cubed minus 30 times negative 1 will give us negative 30. If I plug in positive 1, so jumping down a little bit, we're going to get positive 30. Oh, is this really symmetric? I guess it would be symmetric. We plug in negative 0.5. We'll get 7.5. Well, symmetric, but the signs are different anyway. And then plugging in positive 0.5 will give you negative 7.5. So we'll get negative, positive, negative, positive. And I've run out of space to write an answer. I'll squeeze it down in here. So we have inflection points at essentially all of those, because at all of those 3 critical points, I shouldn't call them critical points because that's not technically what they are. At all 3 of those points that we found, the second derivative changes sign. And remember, for the second derivative with the inflection points, it doesn't matter how it changes, it just matters that it changes in general. So we have inflection points at 0 and both the plus and minus square root of 1/2. So that's that one. And that's the last one we're going to talk about, because that's the last one in 4.1 and 4.2. So we don't have as much time as I thought. We have a little over 5 minutes. If anyone has any questions that they want to talk about, we can do that. Otherwise, if you don't have any questions, you can be free to go. But if there are questions, let me know. Hey, Zach, if you hear me, and I know you were having mic things before, and I don't know if your mic is still not working. Can you type in chat? Are you having SI review things?
Yeah, I can hear you. Yeah, so I am holding. I'm trying to get a review test review session tomorrow night, and I tried to get it scheduled for 6 o'clock. So if I can get that approved, I'm still waiting on approval for that. If I can get that approved, then yeah, we will be having a test review tomorrow from 6 to 8. If I can't get that approved, we're still having an SI session, and it will be a test review, but it will only be an hour long at 5 o'clock.
Okay.
And to all the students, I will be sending something via Remind as well as through an email, just reminding you guys what times and a link to where you can find the video.
Cool. Thanks, Zach.
Yeah, not a problem.
Yeah, Ami, do you have what number it is?
And I gotta pull it up real quick. So that'll take me a second. But you can talk about one of the homework questions if you want. Nope. Da-da-da. Gotta pull up the homework. Do-do-do-do-do-do-do. 4.1 question 25. Okay. I just gotta get to it, but I'm pulling it up right now, so one moment. 4.125. You like have it on me. You just don't know you have it. All right. So we have this function. So this you might have different numbers on yours, other people, but this is 4.1 number 25 on the homework. So you first needed to find critical points, which you did correctly, Ami. So I'll kind of breeze through that. So we need the derivative here, which would have been a quotient rule. So if I do that super quick, 2x, so we'll have f prime times g minus f times g prime. Whoops, getting ahead of myself. All over g squared. If we simplify that numerator, since that last piece is 2x squared, we'll get x squared minus 2x squared, so 16 minus x squared all over x squared plus 16 all squared. I'll hopefully have time to do that, Jackie. So we want to set this equal to 0. Remember, I gave us a little shortcut that if it's a fraction, you just need to set the numerator equal to 0. I'm doing this somewhat quick because we're slightly running out of time. And then we need to find if the derivative is ever undefined. For the undefined piece, you would need that x squared equals negative 16, which doesn't happen because we can't take the square root of a negative, so that would never happen. So we need to just focus on setting the derivative equal to 0, which would give us 16 equals x squared, so x equals plus or minus 4. So then we need to figure out whether they're maxes or mins. So that's when we plot them here, and this is where we seem to be missing some things possibly on me. So we need to choose some test points. I'll slow down a little bit. So let me pick 0, I don't know, 5, and negative 5. So we need to plug them into the derivative. So that's this 16 minus x squared over x squared plus 16. So if I plug in, let's start with negative 5. We'll get 16 minus 25, because negative 5 squared is 25, all over 25 plus 16 all squared. 16 minus 25 will give us negative 9 over some positive number. Let me figure out what it is, though. Oh, geez. 1681. But this is negative. So when I plug in negative 5, I get a negative. When I plug in 0, 16 minus 0 over 0 plus 16 all squared will be 16 over 256, which is positive. Plugging in positive 5 essentially gets us the same thing as plugging in negative 5 in this specific case, which will get us the negative 9 over 1681 again. So we'll have a negative. So we have we're decreasing, then increasing, then decreasing. So essentially, oh no, don't do that. No. Cortana. No. Anyway, so sorry, sometimes I randomly press my Cortana. So the -4 turns out to be a min because we are going from decreasing to increasing. And then equals +4 turns out to be our max. So Ami, sorry. The only thing that looks weird is you have eyes floating around in your answers and should just be 4 and -4. So the max should just be +4 and the min should just be -4. So you're pretty much there. Just the notation. I don't know where those eyes are coming from, but whoops. So we're out of time. Jacqueline, if you can stick around for another minute or two, I can totally answer that question. But everyone else, technically our time is up. Feel free to leave. But Jackie, if you can hold on a second. 4.132. 132. Jack, I forgot about this one. Jackie, you have it right. It's just the notation in Wiley. Did you lose any? No, you haven't lost any points yet. Okay, cool. So you wrote in, and good thing that you kept them capital because that's what you wanted. So this is what you typed. This is what Wiley is reading that as. So what you want to type in is you want to put some parentheses around that 2A. And that's it. So you have that perfectly right. It's just the notation in Wiley isn't accepting it. All right. I do have a class in a few minutes, but if anyone has a quick question that they want me to go over as well, I can stick around for a few more minutes.